It's always been a joke in medicine that you can diagnose everything in the brain, but you can't treat anything. And part of that has been that you can't get to the brain. We're not all the way in the brain. We're sort of sitting in a blood vessel on the brain. So we're sort of somewhere between Neuralink and a scalp base. BCI struck me as something that was, if it worked, was going to be hugely revolutionary for the field of neurology. The patients who we're trying to serve are people who are paralyzed. And this is the first wave of BCIs, is to take out a live signal and achieve a control signal so that you can control stuff without having to touch anything. So who would benefit from that? People who are paralyzed.
We need people to think about what's possible and explore applications that have not been built yet.
I think the holy grail of the future really is, in my lifetime, nuclear thermal propulsion.
And the only way the science fiction future happens is if we make it happen. Hi, folks. Welcome back to The Long Frontier, where we get into the overnight successes, 10 years in the making, that are turning science fiction into science fact. I'm Abe Murray. I'm here at AliCorp, where I invest in deep tech, aerospace, space, robotics, energy, all the cool stuff. And we meet the best founders who are just doing the most incredible things, and we love to share them with you. So we've talked about space, we've talked about biological compute, and today on The Long Frontier, Brannon will tell you what we're digging into, but I'm very excited about it. Brannon?
I'm Brannon Jones. I'm also at AliCorp with Abe, and very excited to jump into the deep tech technologies that are going to change the world. So the one in particular we're going to talk about today is brain-computer interfaces. So for 7,000 years, humans have been drilling holes into brains or through the skull to get to brains to try to change neurological conditions and improve human capabilities. But mostly for the last 7,000 years, we've had no idea what we're doing. That is starting to change. There are a number of players emerging who are able to read those signals and are giving real capability back to people, to put thoughts onto an iPad, to allow people to think and write on a cursor, to be able to move external limbs. This is the world, the current state of brain-computer interface. And today we're going to jump even further into it. The science, the surgery, the companies racing to build it, where it all goes from here. So I am extremely excited to introduce one of the people who is actually at the frontier of doing it, Tom Oxley, CEO of Synchron Technologies.
Thanks for having me.
I always love to start with just tell us a tight bit about yourself and how you got here and what got you excited about even digging into the space of BCI.
Well, I'm from Australia originally. I did my medical training. I learned internal medicine, and then I started in psychiatry, moved into neurology eventually. And then I first read about brain-computer interfaces when I was just about to start my neurology residency, which was back in 2008, 2009, a long time ago. And that was around the time the first report of a human implant had been reported in Nature magazine by Lee Hochberg. Actually, it goes back earlier than that. Philip Kennedy reported a first human implant back in 1999. And then Hochberg in 2006, I read about that in 2008. And I had the idea at that point around not doing open brain surgery to build the device. And so and then it's been a journey of 12 years since then to where we are now.
And it's crazy because to me, 2008 feels like yesterday, but to folks showing up today, it might feel like forever ago. In an earlier episode, we looked at brain computers and kind of talked about just the general approach to how do we understand the electrical signals going on inside of brains. Goes back to the late 1800s when people were starting to poke around with, can we keep brains alive? And then, the Utah array was developed in the 70s and computers got more powerful in the 80s. So it's been a whole ramp of technology that got us to the point where people could dream dreams like yours. I'd love to hear in your words just what the brain-computer interface industry even looks like. Like what's been going on? When did it really start? And what made 2008 the year that you could start dreaming these dreams?
Well, it's been around for a long time, the concept of a BCI or a BMI, brain-machine interface or brain-computer interface. A lot of early work using scalp-based EEG, detecting the very early scalp-based EEG systems used particularly a signal called the oddball response, which is quite a large brain response if something weird happens, if you detect an unexpected abnormality. So that was used to sort of generate a blip that was then used to control the speller. And then through the 70s, 80s, and 90s, a lot of animal work starting to delve into implantable BCIs. And then we moved into human testing with the Utah array. The first Utah array in a human was in around 2004, published in 2006. So, I mean, the general concept is that there is an electrical signal from the brain detected with a sensor either on the top of the scalp or inside the brain, or deep in the brain, or on the surface of the brain, or in a blood vessel, or on the scalp. There's a whole range now of different sensors, but they all basically try to do the same thing. Record a real-time electrical signal that is associated with some brain state and convert that into a output that can let you engage with some external system. So for me, I think like the term BCI has become a little bit synonymous with neurotechnology, and it's kind of started to wrap up brain stimulation and a whole range of other things. But I think for the purists, if you're a purist on BCI, it would be around the primarily use of a sensor, detect a brain state, and in real time, and then transmit that to an external computer and let you engage with an external system directly from the brain.
So can I actually ask you then, based on what you were saying before on reading those brain signals, just to give the audience some context, why is it hard? Why is it hard to read brain signals now? What are the fundamental trade-offs or challenges that we have to overcome to even have BCI devices?
Well, maybe starting with the split between implantable and non-implantable, which for the most part means being under the skull inside the cranium or outside, because it's the cranium that probably has the biggest signal attenuation dampener effect. So then you've got skin and dura and some other elements, but the bone is the big dampener. So if you're on the outside of the bone, you're basically limited with the range of frequencies that you can detect. And if you're limited on the range of frequencies, you're recording from much larger brain regions. So the scalp-based systems are detecting lower frequency systems. That's why they're often about arousal states or meditation response or kind of alertness. They kind of base level.
That doesn't need as precise reading or something to get that. You can read a smeared signal and understand arousal or
right.
Say more.
Correct.
Okay.
Correct. You can see these background rhythms that reflect broader based systems like arousal, but it's harder to detect more focal activity, and also the time resolution is often not as good on the outside. But then, interestingly, even despite that, there are some signals that are quite useful. Like I mentioned, the oddball response. That actually what I believe what turns out to be one of the biggest challenges of an EEG is that to get really clean signals, you have to use these wet electrodes. You have to ideally shave the hair, but if you don't shave the hair, put some gel down, get the array or the sensor really close to the skin, and then make sure it doesn't move. And so there's been a big challenge over. And even if you do that, having a system that is always there, always on, and always recording brain activity is obviously very hard to do because you have to take these helmets on and off. So it sounds like it shouldn't be that big of a problem, but I think the wearable problem of external BCIs is actually a major challenge because you want a stable signal, and you can't get that from an external. So that's a big challenge on the wearable side.
And I'm properly dorky enough that we have a 16 electrode EEG cap downstairs. It's got dry electrodes. They don't work well enough. We had to go to wet electrodes. I don't have a bald head. It's super messy. And even when you get all that wired up, you get so much RF interference from the cables, and it's like really hard to pull out these very weak brain signals through that cap. I'm curious because my dream is that I could just wear a cap or some kind of thing, right? The reason we're talking is because I want to live in a science fiction future. I read Neuromancer. I read Snow Crash. Everybody's watched The Matrix and The Variants. We want to live in some world where we can just do magic computing direct to the brain. And I don't want brain surgery, probably, but maybe. So I'm just curious, like going back to that EEG, the wet electrodes, the things that we picture when you maybe have seen a picture of somebody wired up. Is there any better path there? As you look at the industry and people working on that, and as these phones become better and technology becomes better, are we going to be in a world where we can get better signals over the top of the skull? What do you see happening there?
The question is still there. When we joined an implantable BCI program back in that was US defense funded, DARPA funded back in 2012, and that same question was being asked back then, and a lot of capital deployed at that early stage of funding to answer that question. We've seen various iterations come through. Emotive, I think, have done really well. Kernel came along with it, not an EEG signal, FNIRS signal, trying to solve that problem. But I feel like there hasn't been any consumer product that has come out that has solved a particular real-time control. The best I've seen are around the meditation and kind of arousal state feedback, maybe attentional feedback. Apple has some patents on this. They haven't released any products yet, but I know that they've got some patents on using AirPods to try to probably record some level of arousal state, maybe attentional shifting or oddball response. And now we're seeing there's some companies that are now amassing together huge populations of EEG recordings, building foundation models. For instance, there's a foundation model called Zuna by a company called Ziffer that came out recently that was a pretty impressive large foundation model. The challenge with, and then Meta's been doing a lot of work on this as well. This is a field called neuro AI that's now emerging, which is the use of aggregated brain data to try to build foundation models. And the idea with the foundation model is that you can fine tune on certain types of tasks or brain states. But the challenge with all of these is that if you're going to build a foundation model, you then want to be able to probe the model. And so to be able to probe the model and do something with it, you need to have it running live. So you have to solve the challenge of a kind of robust, dependable, stable signal. And I think that's been a huge challenge with anything that requires putting something on your head. We're not all the way in the brain. We're sort of sitting in a blood vessel on the brain. So we're sort of somewhere between Neuralink and a scalp base. Like we're on the other side of the bone, but we're not inside the brain, in a blood vessel on the surface of the brain. But one thing we've realized is any element of our system that has a wearable, because the patients who we're trying to serve are people who are paralyzed. And this is the first wave of BCIs, is to take out a live signal and achieve a control signal so that you can control stuff without having to touch anything. So who would benefit from that? People who are paralyzed. So as soon as you take people who are paralyzed, if there's any wearable component, it's immediately a huge challenge for them. So, and a lot of the BCIs now have, like, if there's no battery, they've got to put something on. Even a recharge requires something. So, even compared to the headpieces, on the scale of like implantables, what's become obvious to me now is the systems that are going to be most useful are the ones that are no touch whatsoever, which includes being able to wake up and turn on your system without touching it, without putting in your password, without picking up your device and putting it up for facial recognition. Everything's got to come straight out of the brain. So these are some of the challenges that we're facing. So I think it just speaks to that. I would rise to even if you got the electrodes working perfectly on a scalp-based system, it's got to be like kind of locked in and stable and just stable is one of the biggest challenges.
And there's a lot to be said for that. Many people don't like to wear a watch or a hat, and any system that requires some kind of constant contact around the brain probably won't be as nice as an implantable. I'm curious on the foundation models, is the idea that, if we could just record enough signals up here and map them to things we know are going on inside your brain, we could overcome the signal smearing and the poor signal to noise ratio and just have a perfect interface?
Yeah, signal to noise is one of the major advantages of one of the major promises of a brain foundation model is immediate calibration, immediate noise cancellation.
Yeah. So you brought up what you're doing at Synchron, and I'd love to explain more about how you came up with that concept. And just, it is science fiction. Like what you just said is you're somehow putting brain computer interface into a blood vessel, into my brain, above the brain, below the skull. That sounds crazy. I'd love to hear more about it, how long it took you to get here, kind of the state of the art where you're at, and just get that. And then I'm going to pull all kinds of threads on it.
Yeah. So, in 2008, I saw the Utah Array paper in Nature, which was a couple of years old at that point, from 2006. And I was, at that point in my career, I was just early in my medical career trying to decide what to do. And I loved the brain. And I saw another field that was emerging in the field. So my co-founder of Synchron, Rahul Sharma, is an interventional cardiologist at Stanford now. And so back then, he was all obsessed with interventional cardiology, which is the field of putting catheters into your body, so putting in pacemakers, putting in stents, anything that you can put into now, valve replacements, which used to require open heart surgery. So that field has really become a very sexy, hot field over the last few decades, since the 80s. It exploded in the 80s and it became super hot, and the growth has been crazy. And so there's now 1 million stents, 1 million pacemakers, and very successful, fast-moving, high technology pace field, all catheter delivery-based stuff. And that hadn't happened in the brain yet. There was a small field of putting catheters through the blood vessel going up to the brain to treat aneurysms. And that was about it. There were some other vascular malformation diseases that were treated, but it was still a very small area back then. And then I thought, well, if BCI, I think BCI struck me as something that was, if it worked, was going to be hugely revolutionary for the field of neurology, which has traditionally been considered to be a field which there is not much treatment. There's now a lot of pharmacy and drugs that are now appearing for various conditions, but by and large, it's always been a joke in medicine that you can diagnose everything in the brain, but you can't treat anything. And part of that has been that you can't get to the brain. So when I read about the Utah Array, I was like, that is phenomenal. It's just like when you first, people always have an aha moment when like, is that real? Is that possible that you can put a sensor in the brain, create a live stream, and then do something with that signal on the outside? That seems crazy. It feels like science fiction. And then, so I saw the Utah Array, I thought that's wild if this works. But then I immediately thought, well, looking at cardiology, open heart surgery was always a dwindling field. So cardiothoracic surgery has shrunk, not grown, while interventional cardiology has exploded. So my co-founder and I just said, well, if BCI is really going to be that big and it's going to serve millions of people, the only way to do that is you have to get out of the operating room, because you can't scale by delivering therapies in the operating room. It's not so much that people don't want it, it's more about the economics of scale and the limitation on resources in the hospital. It's very expensive to go into the OR, and it's a very limited resource. So that was the thesis from the very beginning, which is held as the core thesis now for Synchron, which is, what are the ways that we can deliver sensors into the brain that avoid open heart surgery, and most importantly, are deliverable in the cath lab? So that was the early thesis. And then what did happen over the last sort of 10 years now has been that, and this is what I trained in. So I went on to do neurology. I actually became an expert in stroke. And I then came to New York to take on a endovascular neurosurgery fellowship and how to do these procedures. And in the year that I was doing my fellowship, a device became approved that could go up into the brain and pull out a blood clot that caused stroke. And it's honestly one of the most incredible things you'll see in medicine. You have a massive stroke, which is a blockage in an artery. Patients will come into hospital, can't talk, slumped over, drooling, on the pathway to either dying or going to a nursing home for the rest of their life. You put up this device, you pull out the blood clot, restore blood flow, and they come back to normal within like an hour.
It's incredible.
And it became the biggest breakthrough in stroke neurology ever. And that happened the year that I came to New York. And I'd already spent 4 or 5 years building this device through the blood vessels. And so kind of overnight, this field exploded and has now almost become as not popular, but like as large as interventional cardiology now. So the field of interventional neurology or neurointervention has now exploded because of this huge stroke breakthrough. And so we have been slowly building to sort of take that and now progress that innovation cycle to now be delivering sensors into the brain.
That's amazing. And I want to ask you more about the endovascular approach and some of the trade-offs there. Before we get fully into that, let's close the loop on the other invasive methods. You talked about Utah Array, talked a little bit about Neuralink. Tell me just some of the advantages, like what would their argument be for why you got to go inside, despite what you mentioned, hard to scale, high cost? And then are there any others, surface cortical, and how do you think about how those play?
Yeah, there are huge advantages because there are advantages from an electronics perspective. So you want to put your analog to digital conversion as close to the source of the signal as possible. Otherwise, noise gets introduced in the distance from where the sensing is to where the chip lives. So the shorter that's possible, the better. And the other thing is, if you can open the skull, your chip size, your electronic size can be basically as large as you want. Now, obviously, you're going to get it as small as you want, but from our perspective, we have to get things through like less than a 2 millimeter hole to go through a catheter. Whereas if you open the skull, you can put a chip package, which doesn't have to have that constraint. So that's the huge advantage. As of today, that would enable you to have higher quality recordings, more channels, and high quality signals. And then the other advantage is, Neuralink. So there's Neuralink, which has chosen to have like a sewing machine. So they insert threads that have like 16 electrodes in a thread, and they inject that down into the brain. So it's recording at different layers, and they inject those in a range of areas. Paradromics is second or third in line. They have stiff shanks, very similar to the Utah Array, but with modern materials. Precision is next. They chose not to penetrate into the brain. They still cut into the skull. They say it's a smaller hole. We haven't yet seen what that's going to look like when they implant something in a human. But they're saying so they put a surface array on the surface of the brain. There's a group called ECHO out of UCSF, led by Eddie Chang, who also do a surface array. I think there are going to be some differences in material between the ECHO array and the precision array, and maybe the size. And that kind of gets us onto an interesting conversation to talk about one of the elements here, which is how much coverage of the brain do you need versus electrode density?
Yes.
I'm very curious about that one. Well, two related questions. One is, in all of these invasive approaches, my understanding is the brain eventually has an immune response to it. So your signal might degrade over time as your brain scarifies around the intruder. I know some people are working on different elements that might kind of trick the brain, doesn't look like a foreign object. But that seems like a challenge. And I'm curious if your approach through the through the blood vessels avoids that. But also what the solution is to that scarification, over time.
Yeah.
Do you have to just keep going in and replacing these things?
So the argument in the field is that if you penetrate the brain into the actual brain tissue, there is a very particular immune response that is driven called gliosis. And gliosis is like a foreign body reaction. And unlike, say, with skin or endothelium, where if you put like a splinter or something at the base level of the skin and it grows over it, it'll just stay there. The brain never stops. It won't form collagen and stop scarring. It'll just continue to form scar tissue as long as the foreign body is in there. And so what happens with the implanted arrays, you get a buildup of tissue around the array that starts to push the sensor away from the brain. That's the theory around why the you start to get signal loss over time with penetrating arrays. Neuralink will argue that if you make the device soft enough, that it won't generate the trauma, which leads to the gliosis. I think that remains to be proven, but that's their standing thesis. Precision and Echo would argue that that's why they've chosen to not penetrate, but instead stay on the surface. So it's interesting. If you go penetrating down, you can record from single like neurons. They're called spike recordings. If you go up to the surface of the brain, those neurons exist in columns. Like think of like a bunch of tiny noodles all packed with each other. Yeah. And these columns fire often together. And if you have the electrode on the top of the column, you can record quite fine. Now, you're not going to get spike recordings, although some would argue you can get spike recordings, but you can estimate close to spike recordings, but probably not. It's instead called local field potentials. And so if you record from a local field potential, which is the amassment of these columns, one of the debates in the field right now is how fine recordings can you actually get when you're sitting above these columns? And Precision are arguing that they're getting really fine. I think they're down to 50 micron spacings. But these columns are something like, I think they're like 300 microns, so like 0.3 of a millimeter, these little spaghetti columns. So there's a debate in the field right now with what is the right amount of electrode spacing. Because if you use up all of your electrodes in a tiny area, you want to make sure that you've got independent information from each channel. Otherwise, you've oversampled with your electrodes and you've lost an ability to get independent information. So I think what Echo are doing, or what Eddie Chang's group in UCSF have shown, is that their original academic work was more in the domain of 3 millimeter spacing with their electrodes on the surface. I think they might be getting smaller now, I'm not sure, but I think this is a really hot topic right now. My personal view is that we would much prefer to have, now in the blood vessel, it's different because we've got another layer of blood vessel tissue. So we don't get as fine recordings as being right on the surface of the brain. So we've spaced our electrode around 3 to 4 millimeters in the stent. And we're trying to record from motor area, sensory area, premotor area. And our goal is to get a basic joystick navigate, like D-pad, up, down, left, right, A, B from that's what we're trying to target for our device. We think if we can deliver that for our patients, it's life-changing and could be a very successful product. But as we go into the future, the goal of BCI is to record from as much brain as possible. And then I think we start to get into what's becoming the apex thesis in BCI, which is that can you develop foundation models of cognition? Now, we're starting with motor control. If you want to do a joystick, you go to the motor area, which is a control signal. All the companies are starting with motor control. Neuralink's moving into stimulating for vision. My view is that I think the biggest value item in these devices ultimately is going to be recording from multiple brain regions.
Yes.
Building over time a foundation model of general cognition, which would require multiple brain regions, where when I say foundation model, it generalizes, but it also is able to predict the next token of cognition, which would enable supplementation of cognition. And so in order to do that, you have to get to broad brain regions. And so we're thinking at Synchron that actually we would prefer to get wide dispersion of electrodes across multiple regions rather than focusing all of the electrode density into one small domain, because that can't scale across wide ranges. So we think that coverage is becoming a more important feature of how to result in a general model of cognition.
And just to dig in a little bit on that point, with your endovascular approach, do you feel like it's easier to get to all of the brain because you're already in this highway of blood vessels that are supplying the entire brain, whereas with everyone else, it sounds like it'd be multiple surgeries all around your head? Is that kind of the delta that you're talking about?
Yes.
So,
yes.
And then it also sounds like the fundamental bet you're making is, hey, if we not only scale the area of coverage, but we make it so easy to do, it's just a stent, that we get many more patients, that you feel like over time you'll be able to overcome the advantage of having the actual electrode implanted into the brain, reading the spikes from a single neuron or from that single column of neurons, that you can overcome the lack of quality of data. And already we know it's higher, much higher quality than non-invasive. But you can overcome the lack of quality of data relative to the other invasive approaches with scale, with AI. That's kind of the bet. And I think
yes, but my personal view, that's accurate. But my personal view is that I do think that staying on the surface of the brain is the sweet spot, because unless we come up with some way to turn off the immune modulation that happens in the brain, I think it remains to be proven that penetrating arrays can withstand a longevity, beyond months to years. So I think let's see what happens in that domain. But I would bet on achieving wide coverage, staying on the surface of the brain, and getting to multiple brain regions. I think that's the sweet spot. I think that's what's going to that's what I think will be the ultimate.
So and then, well, let me just ask my final question. Then after all that, are there any methods of using BCI that are not, that you cannot do if you do not measure that individual activity of individual neurons? Or is there a bandwidth region you just can never reach? Is there an application that would not happen if someone's wearing this and wanted to, type as fast as they're thinking? Is that limited to only particular modalities, or then still with scale you can handle those kinds of challenges too?
That's a good question. The other approach that we haven't mentioned, if Max Hodak was here, he would say to get to that level of fidelity, you have to get to the biohybrid domain. And so I think he would argue that his approach, which is a longer term vision, is that it's going to be biological, like grafting cells. So I think the idea would be that you grow your own cells, you grow your own brain cells, basically put it onto a scaffold, put it into the brain, and then have those cells grow and multiply to then create thousands, hundreds of thousands, millions, billions of connections. I guess what you're asking is, with regard to penetrating versus surface array, is there a limitation on what the surface array can do relative to the penetrating array? I would say yes, because it hasn't been proven yet. Surface arrays, Eddie Chang has shown pretty good speech detection, and there's been shown pretty good control of cursor control. But Neuralink has still, I would say, got the best cursor control that's been demonstrated so far.
From going deep inside and listening at that neuron level,
they're
and
not
just
deep.
having more information.
I wouldn't say they're deep. They're still very superficial, but they're penetrated.
Okay.
So I think it remains to be seen if we can achieve that level. But I think on the flip side, the jury's out on whether the Neuralink device is going to remain stable and keep working over a period of years. So I think everyone's waiting to see what that evidence looks like, and they don't publish a whole lot. So there's the community is hungry for Neuralink to do more publishing to sort of see what's happening.
Well, it's an exciting moment where all of this was science, dreams, like you said, 2008 just became possible. And now here we are in the second decade of work on this, and it's becoming, real chips and real humans doing real things. And I think you're on your way there. To confirm, when you go in through the blood vessels, you don't get that gliosis. You aren't getting a immune response to it. So you just sit there and have whatever signal fidelity you have for the long term. Is that what we believe?
Yeah, but that's also the same for the cortical, the surface arrays on the brain, is that the argument is they don't also get the gliosis. It's only when you penetrate into the brain tissue that you start to trigger that gliotic response, is the theory. There's still adhesion and like scarring, but it's different.
Okay. I'd love to imagine, it seems like what you're doing will work, right? And like you said, the ability to go inside through these blood vessels has unlocked, a whole industry around brain health, brain surgery, and you can piggyback on that. And you're starting in the motor cortex. A D-pad would be phenomenal. I would love that, right? Anything to let me not have to talk at my computer or mush my fingers around to make ideas go into the computer would be pretty cool. And you spoke to wanting to hit more surface area. Where do you see Synchron going 10 years, or the industry going, add 10 years, add another 10 years, what would be the ideal kind of theoretical maximum? If we could, we should. Would you want to put hundreds of these things across the brain on the surface and every blood vessel you could get access to? Are there just a couple distinct brain regions where you're like, look, we just need 20 of these and we've got, the 80% answer to it, and we can get there faster than people think we can once we get going? How do you see this thing shifting? Is it a long, slow build, or does it all happen suddenly? When you dream your futurist dream, where do you see this going?
So we've seen motor control proof. We've seen speech detection proof. Vision is being worked on. I think what's intoxicating for me is to think through what the rest of the prefrontal cortex is doing in humans. And you go and try and read about it, looking at the whole body of work with functional MRI. So, fMRI has been the sort of gold standard tool to unlock the functional localization of brain areas in association with certain tasks. And so we know the left frontal lobe is around communication, but also planning, mathematics, logic. And the right side of the frontal lobe is more about nonverbal, emotional, personality, singing. I think it's going to be, but none of the tasks really get to what's actually happening there. It's kind of been a very, very viewed window into how it works. I think it's going to be when you put a BCI onto the prefrontal cortexes and then watch it over time to see what it was doing when certain things happened during your day, that I think is going to unlock huge potential to engage with architectures. So I think I think the vision for BCI from my perspective is that the BCIs serve certain purposes that are domain specific, say motor control. But once they get to broader regions and we build these sort of individualized foundation models that start to understand how your brain reacts given certain, contextual clues, then my vision or dream is that we could supplement. And so I think there's kind of where we are right now, which is paralysis, maybe now looking at vision or speech disturbance. And then there's this kind of immediate jump to, it's going to then be the, neuromancer future is what's coming next. Human 2.0 is next. But I don't think that's what's going to happen. I think there's going to be a middle step, which is a broader application in scale in healthcare. And I think if we have a general cognition model that can make predictions on how you will or want to have engaged cognitively in a certain task, and you fail, such as with cognitive impairment, cognitive decline, age decline, mild cognitive impairment, or even Alzheimer's, which I think all those categories I just listed amass to about 500 million people in the world, especially age-related cognitive decline. If the system is up and running, kind of think about it like your brain on autopilot. It's like it will detect when you're trying to do something and failing, and then supplement your cognition, maybe a failed word, a memory that's forgotten, a navigation that you can't get, an emotion that wasn't expressed, any number of those things. It could start to make a prediction and help you overcome, like sort of supplement your cognition in that moment. And I think that could become huge product. Then maybe if that goes well, then I think we're starting to talk about people maybe thinking about doing it. I find it hard to imagine a world where everyday people are going to get these implants. I'm a futurist, I think about it a lot, but I just think there are risks. There are still risks, and there are, there's people need to get comfortable with the technology. There's certainly a lot of first adopters, but you want to know that it does a bunch of stuff. And I think there's going to have to be multiple generations through healthcare before it starts to get used like that.
But to get to that future, it actually feels like your success is going to be key. And some of the things Synchron is doing right now, you guys are the leaders in the field. You guys may be likely to be the first to get your pre-market approval. big pivotal trial coming up. Would love to ask you about that. Just what are some of the things, in plain terms, what do you need to prove? And what keeps you up at night about it? Because I feel like it'd be a massive unlock for the rest of the BCI industry if you're able to be successful with it.
Yep. So the challenge right now is that for implantable devices to get to pre-market approval, this is a fundamental challenge with the regulatory pathway that exists. Typically with a medical device, you design it, you test it, you lock it down, you put it in, you come back a couple of years later and you check, did it sort of improve the symptoms of the disease? With BCI, and I think it's happening with us, I'm pretty sure it's happening with Neuralink from, if I'm reading between the lines right now, is that we all want to keep making improvements. So we've just got our approval for our second generation device, and we've done a bunch of stuff. It's got Bluetooth, it's Apple native, it's got a battery, it lasts a long time, but we made a bunch of changes. And now the FDA is like, oh, okay, changes. So start the clock again, and within various domains. So that's one element, is how is the field going to handle the constant iterations and changes and have the FDA kind of not sort of keep going you back to zero again. And it's interesting right now because of what's happening with China moving so fast, where they've got a much more flexible regulatory approval process than what's in the US. So I think there's a fundamental, so that's one. The other thing that's fundamentally challenging with BCI is typically with a medical device, you put it in, turn it on, and you come back and you measure the change in symptoms of the disease that you're treating. What are the symptoms of a prosthetic device that overcomes paralysis? It doesn't actually, a BCI that gets used as a communication device, it doesn't fix ALS. It doesn't fix spinal cord injury. So how do you measure ALS? You normally measure the arms to get a sense of how strong the motor control of the arms is, or spinal cord injury. You look at the legs and the body. There's no mechanism of assessing the recovery of the motor control that comes directly out of the brain because you can't see it, because the field of neurology is about assessing what's physically available. And so we're dealing with patients who have limited physical ability, but the BCI doesn't improve your body. So then it's like, okay, so you should just measure the output of the BCI, right? Well, then the FDA would say, sure, but we want to see a validated scale of what that looks like. And that doesn't exist. And then every time you make a slight change to the system, you're measuring it in a slightly different way with different outputs. So there's been and this is a hot topic right now with regulatory approvals, with where we are in Neuralink are at and all the other companies are, what are the clinical endpoints in a clinical study for this? So over the next few years, and then the other issue is, I think what we're realizing is that the number of patients who the FDA has let us work with is very low. And in a typical medical device, that might be okay. But with BCI, where you need data collection to build the models, to build the product, we're starved of data. And so the product development that requires large amounts of data is starved. Again, which China is going to open up the aperture relative to what's happening in the US. So I think there's also a dialogue with the FDA right now with there are people who, particularly in the field, if you have ALS, you've got a short life expectancy, you don't have any means of control, and the FDA is playing a very paternalistic role in saying, we really want to make sure that all of the safety considerations are completely understood before we let you do this with more people. And it feels like the level of safety concern for the FDA is, I get it, I respect it, but the patient's not able to make a determination of whether they want to take on any risk, especially if companies like us, who are very transparent with our data, publishing a lot. We've published about 30 papers. We publish everything that's going on. We've published all of our safety concerns with our device. Trump released Right to Try, which was an act that let people try, if they had a life-threatening condition, let them try medications that are very early and not proven out and take on the risk themselves. That doesn't exist for medical devices. And I think that would be the type of thing that could allow more people to get access to the technology.
Does China making it a national strategic priority for them Do you see that causing the same in the US from the competitive dynamics of saying we're not going to let China have this capability before or do you see any movement rather, either in our intelligence community or otherwise, that might make it a national strategic priority within the Western world?
Yes. So, maybe just to mention it, Brandon, so you obviously read about it. What did you read about the Chinese national strategy for your audience?
I was just reading that they were making it a national strategic priority for them.
Yeah, it was a big deal. It was a really big deal. They've elevated. There's now a 5-year plan. It's been elevated to national technology of interest alongside 6G, AI, quantum. It's BCI is now right up there. And I traveled to China with the World Economic Forum meeting about 6 months ago, and I was blown away. And it's interesting. It's like it becomes, once it's a national technology of interest, it becomes social kind of capital to be working in the field. And so I was in a hospital, and the chairman of neurosurgery invited me, and I gave a talk there. And I was talking to him, and I said, how is the national strategy implemented? How do you feel it? And he said, well, the CCP have a office in the hospital, like just down the corridor from me, and I have to front up to the CCP representative in my hospital once a week and explain how much work I've done this week on all national interest, and BCI is always number one. What have you done this week on BCI, Chairman?
Wow.
And so can you imagine that in the US, where you have to report into the government on whether you're conducting activity on the national interest technologies? So it's everyone wants to do it, and then they're supporting. There's capital support, there's reimbursement support, there's infrastructure support, and they've unlocked the regulatory pathways. It's very smooth getting through regulatory approvals now, and they've just announced their first reimbursement item. So the government's going to pay for these devices. So that's legit. That's absolutely. And they've announced by 2027 they want hardware domination in BCI, and by 2030 they want the sort of top 2 to 3 global BCI companies.
Well, I'd rather see you win that game. And so FDA or friends in the government, if you're listening, we need a path to, stay ahead. We've got the innovators here.
I'm seeing positive things happening in the US government. I think there's people are seeing what's happened in China, and I think recognizing that the US lead in BCI should not be taken for granted, but it is, the pace of development is not on the same curve as what China is on right now. So, but it's a balance, isn't it? It's where's the tech? China's doing it because they have a belief that BCI is going to lend itself towards AI superiority.
I don't think they're wrong.
Yeah, it makes sense to me, the idea that with enough, once we get to multiple brain regions, if we genuinely can build these models of general cognition, is that going to lend itself to models of human intelligence that weren't going to be trained on the basis of words on the internet, but actually needed to be trained on how the brain actually works in the world and learning from how human cognition actually works? And if that lends itself to dominant models, I think that's the bet China's making. So it's tricky to kind of then use that as an argument to change the risk benefit on the individual, because there's this fundamental difference between US and China, between individualism and collectivism. Yeah. And so how do you possibly compete with a culture that's focused on collectivism, where that's going to result in these huge amounts of data collection in the field of BCI that's going to lend itself to that? So
I could flip it around, which is kind of the right to choose is one of the most individualistic things you can imagine. And in America, we're free. So if I'm in that situation, should I have the right to choose to let Tom give me access to an internet?
That's exactly why we think right to try is a really interesting approach here, because that's exactly, I completely agree. And I think where we've gotten out of a well-intentioned place, we've gotten to a place where the FDA is behaving very paternalistically around the individual rights of the users. And I think now you have to provide enough information to the individual. So I think it behooves the companies to be providing that information through data, through literature, and then through consents that are very informed. But I agree, like let the individual make decisions around whether they want to take on the risk. And then maybe the FDA can make a recommendation, but the users should be able to make the final determination.
Well, Tom, I really love this. I could literally pull information out of your head for hours. And I think you're building something really important. It literally is science fiction. And it's been really great to have you explain to our audience how we got here, all the different pieces of it, why you have to go inside and get close to the brain to do this well. And it's actually interesting that we landed on this. And we could go faster if humans made different choices, because I think over and over again, whether it's AI or robotics or other technologies, the things we can do are much more than the things we do. And we as society struggle with, how and when and where do we unleash these things and let them go. So really phenomenal conversation. I'm watching your clock as much as mine. It's just so kind of you to talk with us. Any final thoughts for the audience? Encouragement to study in this space? Whatever, like what would you leave with folks paying attention?
And maybe also one positive story, just because Synchron right now already is giving real autonomy back to paralyzed patients, changing people's lives for the better. So also one moment with a patient that reminded you what you're actually really doing this for right now too would be an awesome way to close out.
Our very first patient was called Graham Felstead. He's passed away now. He had ALS. And imagine being the very first person to like figuratively put your hand up and say you wanted to do this, given the unknown and everything. And his wife, Nancy, was terrified of why he was doing it. Why did he want to do this? And on the first day that we switched on the device and we got him, we were mapping out his body, and it turned out that squeezing his butt gave us this really good initial signal, which he then used to sort of push this cursor around and type out this first sentence. But there was this incredible emotional reaction when he first got it. And we've seen this across all of our patients. The day it turns on, if you imagine having a condition like ALS, where your world is shrinking down, you have lost your privacy, you're dependent on other people around you, you now can no longer use your phone. If the technology opens up that aperture even a little bit, it's this, that feeling when you first rode a bike or you first drove your car, you first got your license and you go for that first drive on your own, the world suddenly feels bigger. Do you remember that? I do.
It just opens up. Yeah.
It opens up. And so after it's shrinking, to just open up that aperture again, that's what autonomy is about. And so it's those moments that make this so they're the most exciting moments for our team.
It's fantastic. Tom, well, echoing what Abe said, thank you so much. Thank you for the work that you're doing. The world needs you to win. We are really grateful that you were willing to give us your time. We don't take it lightly, and we appreciate having you on our show.
Thanks, guys.
Well, that was awesome. That guy is incredibly impressive. One thing that actually updated my mental model that I didn't quite expect was just when Tom was saying that actually the non-invasive approaches that you wear are not as scalable, do not have as much of an advantage as I thought they would. I kind of just assumed that at the end of the day, non-invasive approach would win because everyone would rather wear a headset than have any kind of surgery or injection of any sort. But his point about lack of stability and how that actually can erode the data integrity even further beyond the skull smearing whatever signals you're already losing, I found that quite interesting. I hadn't really thought about the fact that they actually may never be that good because they can't sit and read the signals continuously live quickly enough and with enough integrity because they're going to be shifting, you're going to be hot, you're going to be sweaty, all that. So I will say coming out of this, I became much more of a proponent for the invasive options. Still not sure if I think the penetrating into the actual brain tissue is where I would land. I do really like the endovascular play. He also talked about the subcortical play where you're just laying over the brain too as sort of that hybrid. It seems like one of those hybrid approaches might make the most sense for scalability, but then also in signal integrity. So that was a shift for me.
Totally agreed. And if you followed Facebook bought Control Labs, which is this bracelet you can wear and it tracks, the movement in your arm and lets you control systems inside the Meta Quest or whatever. It works quite well. People like it. But also it doesn't work well when you get sweaty or hot or it's loose or you're running and like it's moving around. So I think there's a, reality to that. We've played with some other systems that are more like sitting over the ears or in headphones and they're cool, but they struggle with that reliability. And I just don't like to wear headphones even, or like things on my head or hats. So I'm with you. I walked into this expecting not to be so convinced by invasive BCI and walking out quite convinced. And clearly Tom's building something pretty impressive, being able to go in through the endovascular approach.
I kind of hate to say it, but I almost would rather have a stent than have to shave my head and put goop on there all day and show up to work like that every time. I'm like, actually, maybe
we've got some wild pictures of my son with electrodes all over his forehead and a grounding clip on his ear, and to get good signal quality out, it's not pleasant today. The foundation models to understand what's going on across the brain is interesting. Yeah. When I was working in health tech, I come out of Google research. We had more data than God. And that led us to incredible AI. And we thought, we'll go do, AI in healthcare. And it turned out healthcare doesn't have big data. Healthcare has a bunch of tiny little data. And I think, Tom said that directly. Inside the brain, we have teeny tiny data, nothing. It's going to be a long time until we have big data sets. But when we do, if you could cover the brain in these, electrodes and pull a ton of information out, then maybe with a foundation model, you could do some clever stuff over the top. But we're so far away from that. And it seems like we're not letting ourselves go fast as a society to close that gap, though China is, which is, I didn't expect that conversation to come up. And that was pretty interesting. I hope we fix that in our country.
Yeah. And I do think it's a little bit about the regulatory paradigm, and just we don't have a way to assess BCI separate from the medical device industry, which you lock the architecture, you do it, you bring it back. Did it fix the situation? It's not the way that AI has been evolving, which is just so much faster. I do wonder if there's a world where it gets classified in both camps. Maybe the actual device itself that's doing the transcription and reading the data is classified one way. People wear it for a certain amount of time, they get enough data, and then you send that data to an AI model. And as that AI model improves, it's what starts to take over the work of reading signals from various devices. And so you have the AI kind of iterating quickly and FDA heavily regulating the devices and managing that process thoughtfully. Maybe there's some hybrid or something like that. But it does, I mean, I guess my question to you is if there was no regulation, is the far future that he talked about, where it's, the eyes, the ears, movement, everything, could that actually be much, much closer? Are we slowing ourselves down? And not for bad reason, but just from a pure physics standpoint, is it the physics limiting us, or you think it's the people?
Yeah, wearing my "I wish the future came faster" hat. I'd like it to be true. My sense is that we're definitely slowing ourselves down a bit with human choices, regulations, et cetera. But I think there's probably a much larger set of actually hard physical problems to solve, technological problems, even surgical problems. How can you get 20 different stents into the blood vessels in my brain in a way that, all the wires fit, the electronics they connect to work, and you're not junking up my brain with stuff that's slowing blood flow? Like, I imagine there's many hard questions to answer. Sure. At the scale of what I would want to control a computer fully using my brain. So it's a solvable problem, but probably, and it sounded like we didn't even get started until 2008, 2010. We're in the second decade of people really working hard on this. The first pieces of this are going to wind up in the world, or already have, but we'll start scaling in the coming years. It's probably going to be a decade before we approach those 500 million people who could benefit from the thing Tom was describing today. So I'd feel like no matter how fast we let the regulatory path go, we're probably still decades from Neuromancer, unfortunately.
Well, at least when you put it this way, think about it. Trepanation has been happening for 7,000 years. People have been drilling holes in the head. So what's a couple of decades relative to 7,000 years? We're 99.9% of the way there.
We'll need to do a longevity episode to find out if you and I can live to see it. All right. This was awesome. Thank you all for listening to The Long Frontier. Let us know what you want us to talk about, because otherwise we'll just keep picking the coolest things we can find.
See you next time.